Good evening. Thank you for attending the first in a series of public dialogues sponsored by UC Santa Barbara and with the generous support of the John Templeton Foundation. These dialogues are part of a 3-year program at UCSB titled New Visions of Nature, Science, and Religion. Further information is available from our website, www.newvisions.ucsb.edu. There is also a sign-up sheet available at the back for our email announcement list. My name is Jim Proctor. I am a professor in the Department of Geography, which is co-sponsoring tonight's event. Our 2 distinguished guests are Evelyn Fox Keller, Professor of History and Philosophy of Science at the Massachusetts Institute of Technology, and Simon Levin, Moffitt Professor of Biology at Princeton University. Evelyn's PhD in theoretical physics from Harvard in 1963 launched a career of interest in the relationship between theory, experiment, and scientific engagement, between physics, biology, and biography, between gender, difference, and science. Her well-known early works are A Feeling for the Organism, the life and work of Barbara McClintock, and Reflections on Gender and Science. 2 recent books include The Century of the Gene and Making Sense of Life, explaining biological development with models, metaphors, and machines. Similarly, Simon Levin completed a PhD in mathematics from the University of Maryland in 1964, and in his positions, first at Cornell University, then at Princeton University, where he serves as director for the Center for Biocomplexity. Simon has maintained an abiding interest in population dynamics, in ecological scale and pattern, in biodiversity and complexity, and in applications to ecological modeling. His book, Fragile Dominion, Complexity in the Commons, applies this lifetime of distinguished research to the challenges facing contemporary environmental management worldwide. Evelyn and Simon's awards are too numerous to list here. Let me just say on behalf of UCSB that we are grateful to both of you for coming to Santa Barbara under what has proved to be difficult circumstances, and we very much look forward to your dialogue. The evening will commence with introductory remarks by Evelyn and Simon. Then I will facilitate a dialogue and question and answer session. If you would like to ask a question, please write it down on one of the index cards our student assistants are distributing right now, and I will present your questions to our distinguished guests as time allows. First, a background on the theme for tonight's dialogue: ecology, complexity, and metaphor. Like its parent program, tonight's event brings together 3 topics we ordinarily think of as disconnected. Ecology, to many people, is the study of the elegant harmony, balance, and simplicity of nature, of how, in contrast to the complexities of our technological species, all of non-human life seems to get along. And metaphor is, well, we all once learned what metaphor was in English class, right? It's kind of like simile without the like. But what does that have to do with ecology or complexity, for that matter? The answer comes from the New Visions program itself. The focus of our program, as suggested in this Earth-Brain image, is concepts or visions of nature, by which we include both biophysical nature, trees and birds and mountains and oceans, and human nature, what, if anything, lies at the core of human thought, emotion, morality, and behavior. Questions about the nature of biophysical and human nature have been central to scientific and religious traditions, and the diverse answers they have provided have resulted in both conflict and consensus, ranging from recent differences over stem cell research to a joint agreement signed by scientists and religious leaders declaring their common support for environmental protection. These questions have been central to many academic disciplines as well, though their answers have been similarly diverse. Our program focuses on 5 particular concepts that illustrate the breadth of academic discourse on nature, spanning the physical and life sciences, behavioral and social sciences, humanities, and theology. Each vision offers a particular synthesis of biophysical and human nature and poses a challenge to commonly held assumptions about nature. The 5 are evolutionary nature, that is, nature is arising from evolutionary processes, which questions the commonly held notion of culture as being distinct from nature and has often been understood, especially in the United States, as a scientific challenge to religion. Second, emergent nature, nature understood via complexity theory as an emergent reality, which has been invoked to provide an anti-reductionistic understanding of complex phenomena ranging from the universe to the mind, to God. Third, malleable nature, nature as subject to human alteration, which challenges the boundary between natural and artificial phenomena, raising ethical questions in the domains of science and religion alike. Fourth, nature as sacred, that is, having significant spiritual qualities, which challenges the distinction between matter and spirit, and as such may be difficult to reconcile with scientific materialism and some religious theologies. And finally, nature as culture, that is, as a culturally based concept which stands evolutionary nature on its head by challenging ideas of nature as being distinct from culture, and more broadly suggests that scientific and religious outlooks are, in many ways, cultural constructions. As you could surmise, some of these visions could perhaps be readily reconciled, but others clearly cannot. Their implications for science and religion are similarly diverse and somewhat contradictory. And all of these visions make some claim to comprehensiveness or universality that leaves little room for accommodation with other visions. So one of the challenges our program faces is in deciding how, or indeed whether, it is possible to come up with new, perhaps more synthetic visions that weave these diverse visions of nature together. And if so, what implications follow for science, religion, and their relationship? One answer to this challenge, reflected in the dodecahedron image here, is that each vision offers a particular perspective on nature, but it all depends on where you are standing, and thus there is no way to bring these perspectives together. Another answer, though, is that each vision is far more limited than its adherents believe, like the famous story of the blind men and the elephant suggested in this image. If all we touch is the tail, we're tempted to believe the elephant is a rope. And if all we touch is the ear, the elephant becomes a fan. Clearly, on this view, we must discard these limited visions of nature and craft new synthetic visions. The moral of the blind men and the elephant is an inspiration, but in practice, it is a tough inspiration to apply. Tonight's dialogue between Professors Keller and Levin offer us an opportunity to witness and participate in this hard work. The theme considers ecology, a realm of knowledge and inquiry which enjoys both sound status as a science and, in some of its expressions, a long history of entanglement with spirituality. Modern ecology is built on evolutionary theory, but evolutionary nature is not the only vision informing contemporary ecology. Simon Levin has played a central role in bringing complexity theory, the core theory of emergent nature, into ecology as well. He argues, as you will hear tonight, that ecosystems, and indeed the entire biosphere, are complex adaptive systems. Complexity theory has been applied far beyond ecology. The back cover of this recent book reads, "Why did the stock market crash more than 500 points on a single Monday in 1987? Why do ancient species often remain stable in the fossil record for millions of years and then suddenly disappear? In a world where nice guys often finish last, why do humans value trust and cooperation?" Complexity theory has, in other words, become a theory of everything to some adherents, a unifying vision for biophysical and human nature. And it has not only taken root in science. A leading scholar defines religion as, quote, "a complex adaptive network." But how are we to understand the sweeping vision in and beyond ecology? Evelyn Fox Keller's major contribution in how biologists make sense of life applies here. We think of science as experiments and equations, but to Keller, much scientific work is inescapably linguistic. She argues that metaphor is indispensable to this activity, and not merely in providing provisional figurative language, while the real business of scientific research is moving toward more literal empirical descriptions. The Greek root of metaphor means to transfer or carry, and metaphor implies a mapping of two domains, a transfer of one onto the other to facilitate meaning. Is complexity, then, the latest metaphoric expression in a discipline where the metaphors of organism and machine have long been applied to make sense of ecological interactions? And if so, are we not moving dangerously close to the constructivist vision of nature as culture in relating ecology, complexity, and metaphor in this way? These are some of the questions Evelyn and Simon will consider in tonight's lecture, and with this background, I will now turn to our distinguished guests, Evelyn Fox Keller and Simon Levin. We will start with Evelyn Fox Keller, whose introductory talk is on organisms, machines, and ecosystems. Evelyn.
Thanks very much, Jim. It's a pleasure to be here. I wish I could see you all better, but the lights are a bit bright, but maybe later. As Jim indicated to you, I'm interested in words, and tonight I want to focus on a particular term, namely self-organization. This is a term that underlays much of our thinking about organisms, about machines, and about ecosystems. And I'll start by asking, what does it mean? The answer to that question, it turns out to be not so simple. In fact, it turns out that self-organization is even more difficult to pin down than the term ecosystem, and subject to such vagary as to lead some to suggest that it is an entirely empty phrase. But it has a history, and a very interesting history of meanings and associations, which I will review, and looking at the changes in meaning in relation to organism on the one hand and to machine on the other. And then at the end, I will return to the question of ecosystems and their relation to organisms, machines, and the concept of self-organization. Now, the history of self-organization is part and parcel of the history of biology, a science first defined as the science of life, explicitly demarcated from other sciences only in 1800. The term was originally introduced in an effort to address the fundamental question of the life sciences, namely, what is the special property or feature that distinguishes a living being from a collection of inanimate matter? In fact, it was this question that first defined biology as a separate and distinctive discipline, what led to the common grouping of plants and animals into a category called life. That is what makes, quote, the two genres of organized beings, as Buffon referred to them, organisms. That what led to all this was a new focus on just that feature, that is, on their conspicuous property of being organized, and of being organized in a particular way. As Francois Jacob observes, it was by its organization that the living could be distinguished from the non-living. Organization assembled the parts of the organism into a whole, enabled it to cope with the demands of life, and imposed forms throughout the living world. But it was only by that special arrangement and interaction of parts that brings the well springs of form and behavior of an organism inside itself. Only that way could one distinguish an organism from its ironic Greek root of organon, or tool. A tool, so how close these concepts were historically, a tool of necessity requires a tool user, whereas an organism is a system of organs or tools that behaves as if it had a mind of its own, that is, that governs itself. Indeed, these two words, organism and organization, acquired their contemporary usage more or less contemporaneously. Immanuel Kant put it with superb clarity. In 1790, Kant gave one of the first modern definitions of an organism, not as a definition per se, but rather as a principle or maxim, which he wrote, quote, serves to define what is meant by an organism, unquote. Namely, again, quote, an organized natural product is one in which every part is reciprocally both end and means. In such a product, nothing is without an end, or is it to be ascribed to a blind mechanism of nature. Organisms, he wrote, are the beings that, quote, that first afford objective reality to the conception of an end that is an end of nature and not a practical end. Organisms supply natural science with the basis for a teleology that would be otherwise absolutely unjustifiable, seeing that we are quite unable to perceive a priori the possibility of such a kind of causality. What kind of causality did he have in mind? Well, he wrote, in such a natural product as this, the organism, every part is thought as owing its presence to the agency of all the remaining parts, and also as existing for the sake of the others and of the whole, that is, as an instrument or organ. The part must be an organ producing the other parts, each consequently reciprocally producing the others. Only under these conditions and upon these terms can such a product be an organized or self-organized being, and as such be called a physical end. Indeed, it is just here that the term self-organized first makes its appearance in relation to living beings, or really in relation to anything. Kant uses the term self-organization to liberate living creatures from the need for an external designer. No external force nor divine architect is responsible for the organization of nature, only the internal dynamics of the being itself. The beginnings of biology thus prescribe not only the subject and primary question of the new science, but also the form of an answer to be sought. What is an organism? It is a bounded body capable not only of self-regulation, self-steering, but also, and perhaps most important, of self-formation and self-generation. An organism is a body which, by virtue of its particular and peculiar organization, is made into a self, which, through its interactions with others, achieves autonomy and the capacity for self-generation. The obvious task for biology, therefore, was to understand the character of this special kind of organization, or rather of self-organization, the property that defined its inner purposiveness, that gives it a mind of its own. At the close of the 18th century and the dawn of the 19th, it was evident to Kant as to his contemporaries that neither blind chance nor mere mechanism, as it was known then, could provide an adequate account of such a phenomenon, and certainly that no machine then available could suffice as a model. Strictly speaking, Kant writes, the organization of nature has nothing analogous to any causality known to us, close quote. Such a science, and indeed such a mechanism, would have to be a new kind of science, one which, not surprisingly, especially given the technology of his age, Kant assumed would be irreducible to physics and chemistry. Now, admittedly, demarcating organisms in the real world was not always easy. For instance, the kinds of organizations that what we call the social organisms gave rise to posed one challenge. Should we, for example, think of an ant colony or a termite colony as an organism? What about a beehive or a cellular slime mold? Humans, too, are social beings. Might we not regard the societies they form as organisms in and of themselves? Aren't human societies also self-organizing? And what about natural communities more generally? Is it useful to think of them, as Frederick Clement proposed in 1916, as constituting a complex organism governed by laws of development? Organisms, both of the metaphoric and the literal kind, are everywhere in the biological and even in the social sciences. As is, although to a lesser extent, the term self-organization. And even in the absence of explicit criteria for delineation, these two terms, organism and self-organization, remained until the 1940s tightly linked. Furthermore, wherever they were applied, they remained clearly set apart from the realm of inanimate objects, especially from those objects that were designed and built to serve human goals, that is, machines. Machines were designed, and they were designed from without. Of course, organisms, too, had long been seen as designed, but even after the argument from design had been laid to rest, talk of design never disappeared from biology. Still now, in the post-Kantian era, the design in question, biological design, the organism's organization, was recognized as internally generated, not externally generated. And the burden, in other words, the burden of the concept of self-organization falls on the term self, for it was the self as source of the organization that prevents an organism from ever being confused with a machine. Self-organization was the unmistakable and inimitable signature of living systems. The first major mutation in this tradition came in World War II. Out of the wickedness of war, as Warren Weaver put it, emerged not only a new machine, but a new vision of a science of the inanimate. A science based on principles of feedback and circular causality, and aimed at the mechanical implementation of exactly the kind of purposive, organized complexity so vividly exemplified by biological organisms. In other words, a science that would repudiate the very distinction between organism and machine on which the concept of self-organization was first predicated. Norbert Wiener called this new science cybernetics, and his vision quickly attracted the interests of a motley crew of mathematicians, physicists, and engineers. Ross Ashby was a particularly important influence on this motley crew. In the 1940s, he built a machine, the homeostat, that was to serve as a primitive model for a brain. Ashby's homeostat showed that a machine properly designed could exhibit autonomous, self-organizing behavior. And this, together with his work on principles of the self-organizing dynamical system in 1947, served as major stimuli for the rash of conferences on self-organizing systems organized by the Office of Naval Research throughout the 50s, well, in the late 50s and early 60s. All of these discussions and all these investigations were conducted with an explicitly engineering aim, namely the design and construction of systems that could organize themselves, grow themselves, and perhaps even reproduce themselves, just like organisms. The crucial property, as people like Ashby or Heinz von Forster formulated it, lay in the relations between the components. It was out of these relations that functionality or purpose would emerge. Frank Rosenblatt's Perceptron project embodied this vision in its most ambitious form, but despite, and that was the project in which Rosenblatt promised that it would be possible to build perceptrons that could reproduce themselves on an assembly line and which would be conscious of their existence. But the project, despite enthusiastic support in its early stages from the Office of Naval Research, in the end, it failed to produce anything approximating a live issue. By the 1960s, support had dried up and the spirit of artificial intelligence, organized around very different principles, had moved elsewhere. The principles, the self-organization principles and spirit did live on, but in other areas of engineering, especially, I think, in control theory. The next important mutation in this history comes with the emergence of studies of nonlinear dynamical systems in physics and mathematics in the late 70s and 80s. Here again, the term self-organization surfaces, but now with a further shift of meaning. For Ilya Prigogine, the term referred to the emergence of dissipative structures in systems far from equilibrium and low in entropy. Given a sufficiently large flux of free energy in such systems, one can expect to see the spontaneous emergence of such striking phenomena as eddies, vortices, or Bénard cells or Bénard rolls. And at roughly the same time, The study of nonlinear dynamical systems by mathematicians was yielding similar insights about these very same phenomena, although here they were described in terms of stable attractors and limit cycles. Either way, self-organization now referred to the production of stable patterns observed in physical and sometimes in biological systems governed by nonlinear dynamics. Enthusiasm for such analyses ran high, generating some quite extraordinary expectations. Paul Davies, for example, wrote, quote, "Mathematically, we can now see how nonlinearity in far-from-equilibrium systems can induce matter," and here he's quoting Charles Bennett, "to transcend the cloud-like nature it would manifest at equilibrium and behave instead in dramatic and unforeseen ways, molding itself, for example, into thunderstorms, people, and umbrellas." The late 1980s brought a noteworthy and indeed much noted addition to these ideas, namely Per Bach's notion of self-organized criticality. Stuart Kaufman's '93 book, The Origin of Order, a book Bach refers to as the first serious attempt to model a complete biology, sought to apply Bach's ideas to evolution, but his vision of evolution operating on what Stu called interacting dancing landscapes, which, driven by self-organizing dynamics, would somehow approach criticality, turned out to be premature. Yet, almost immediately after, Bach did succeed in developing a model for evolutionary dynamics that exhibited all the desired characteristics. Here was a model of an open and dissipative system that organizes itself into a critical state by its intrinsic dynamics, independently of any control parameter. Drawing on an analogy with the physics of phase transitions, the existence of a critical state is said to be signaled by a power law distribution in some variable. The power law distribution was taken to be a clear indication, at least to physicists familiar with the behavior of systems at thermodynamical critical points, that short-range interactions have induced a kind of global organization in which details of the particular system get obliterated. The familiar image, and you're probably all familiar with this, is that of sand being dripped onto a sand pile. And once the sand pile has attained a critical slope, it keeps its canonical shape as more and more sand is added, managing this by setting off mostly small avalanches, but a few large ones as well. The timing and the size of individual avalanches is unpredictable, but their distribution, both in size and in timing, displays the prototypical regularity of the power law. Self-organized criticality soon became a new buzzword, the latest key to an understanding of emerging structure in complex systems. According to Bach and his colleagues, the dynamics of complex systems in nature often occurs in terms of punctuations or avalanches rather than following a smooth, gradual path. Earthquakes, stock market crashes, and mass extinctions in biology are examples of this turbulent behavior. This is a consequence, this is all Bach writing, this is a consequence of self-organized criticality, the process by which large dynamical systems evolve to a state with no characteristic or length scale, close quote. And just a few years later, László Barabasi and his colleagues extend Bach's idea of self-organized criticality to the world of network topology, providing yet another boost to expectations about what the physics of phase transitions might do for biology. Now, here is a literature that begins in the world of physics. It's written by physicists and it's published initially in physics journals, but that rapidly spreads to other fields and is soon taken up by a flourishing industry of science popularization. The term self-organization, as it's used in this literature, is severed both from its original biological meaning, the meaning Kant gave it, and from its later engineering sense in cybernetics. The term now is stripped of all resonances of design in either of the senses invoked in these disciplines, internal design or external design, and appropriated instead for the categorization of complex phenomena arising out of random ensembles, essentially uniform distributions of simple physical entities. Not only eddies, whirlpools, and Bénard cells are to be understood as arising from homogeneous gases, fluids, and lattices, but also more dramatic eruptions like thunderstorms, like earthquakes, and people. Indeed, the emergence of life itself is not infrequently claimed as a self-organizing critical phenomenon. Okay, so what about ecosystems? Or in fact, for more generally, where does ecology fit into this history? I've already cited Clement's analogizing of natural communities as organisms, and probably the next important entry, at least for the history of ecology in the US, is Tansley's concept of ecosystem in 1935. Ecosystems are, in the first instance, systems, explicitly overriding the boundary between animate and inanimate, or not combining them, not so much overriding the boundary, but integrating them. Tansley wrote, "In an ecosystem, the organism and the inorganic factors alike are components which are in relatively stable dynamic equilibrium." And he hypothesized the existence of, quote, universal processes tending toward the creation of such equilibrated systems, close quote. Here is a concept that came out of engineering, and it was not at all obvious to early users of the term whether it in fact made sense to think of ecosystems as organisms. Frank Golly refers to the ecosystem concept as a machine theory applied to nature. But still, as late as 1969, the organismic tradition in ecology was sufficiently present for Eugene Odum to ask, do mature ecosystems age as organisms do? In other words, after a long period of relative stability of adulthood, do ecosystems again develop unbalanced metabolism and become more vulnerable to diseases and other perturbations, like old people? By this time, however, the boundary between whether an ecosystem was an organism or a machine had become somewhat less pressing because the boundary between animate and inanimate had become seriously blurred by the appropriation of self-organization by cyberneticists and its subsequent incorporation into engineering. The actual term self-organization does not appear in Evelyn Hutchinson's classic paper on circular causal systems in ecology, published in 1948, but its arguments clearly drew upon these recent developments in cybernetics. In particular, Hutchinson was interested in natural circular systems and the various self-correcting and self-regulating mechanisms that act to damp oscillations or otherwise maintain stability in the circular causal pathways characterizing complex systems. The term self-organization does not seem to enter the literature of ecology until the mid-'80s, when Howard Odum, brother, employed this term in its cybernetic sense now as a convenient shorthand for the kind of ecosystems analysis he had been doing for decades. But it seems to me that the main engagement of ecology with notions of self-organization comes in the 90s with Per Bach and his arguments for the importance of what he called self-organized criticality. Indeed, Bach viewed ecosystems as ideal candidates for self-organized criticality, and he found confirmation in this prediction in the presence of power law distributions in the size of extinctions. Here, he thought, was a way of making sense of ecosystem development without invoking either the guiding hand of God, man, or even, for that matter, natural selection. The influence of his arguments in ecology and theoretical ecology, I think, was phenomenal. As Sy, Levin, and others point out, however, power law distributions are everywhere. Furthermore, they are not in themselves indicative of any particular mechanism of organization. Sy remains open-minded on the question of the relevance of self-organized criticality to ecosystems, but he clearly recognizes the major failure. He clearly recognizes their failure to consider the effects of evolution on ecosystem development as a major liability. I have to admit that I'm rather more skeptical of self-organizing criticality here than Sy is, but in part because there are many other issues which are also excluded. For example, in addition to the inclusion of evolutionary forces, psi, in fact, perhaps unwittingly, offers a way of improving on the physicist's notion of self-organization when he considers the contents of his desk. And here I take from his book, Fragile Dominion. He writes, quote, my favorite passage in the book, "The contents of my desk may not seem to have much to do with ecosystems, but take another look. My office is indeed a self-organized system with me at its center. It has more the element of design than do ecological systems, yet it still reflects a huge dose of chance and historical influence." Close quote. Now, you might think this is something of a pun, for psi, in fact, is the self who is organizing, or not, as the case may be, his desk. However, it is not customary to include that supremely intentional agent, the human self, in our conception of a self-organized system. And perhaps he should have written, "My office is indeed a myself-organized system." Similarly, we tend overwhelmingly to exclude humans from our conception of ecosystem, or even from nature. But let's stop for a moment and ask, why is that? Why is it that in every conception of self-organization, the self that is the source of organization is, in contrast to the human self, or to the myself, without intentionality or agency? Indeed, if you stop and think about it, such an exclusion seems even necessary, for otherwise, what would prevent us from describing the system composed of engineer and his machine together as a self-organized system? Or from describing an urban landscape as an ecosystem? Now, Psi tries to avoid this problem by downplaying his own agency, by emphasizing the randomness of the processes underlying the design of his office. He's not really in charge. But this is just to sidestep the issue of whether or not agency or intentional design can be brought into our concept of a self-organized system in whatever form that concept takes. To bring the engineer into the system, to put Psi in his office with his agency and intentionality intact, would, I suggest, be to confound the entire tradition which takes human agency and intentionality as a priori unnatural, and accordingly, which pits natural against artificial design. But of course we're natural beings. We are clearly understood by contemporary scientists to be products of evolution, just like other organisms. Nevertheless, tradition, even post-Darwinian tradition, excludes our doings from natural history. It may acknowledge our effects on the natural world at times, though not so often and recently, even celebrate them, but these effects are treated as impingements and not ever as incorporated into our conception of self-organization, or I should say, of nature. Yet to put this exclusion so boldly is to make its absurdity self-evident and to invite us to explicitly challenge the entire tradition on which it rests. So here is what I propose. Let's drop intentionality. After all, this too, like free will, may turn out to be an illusion, like the neuroscientists are telling us these days. And let's focus instead on agency. That's not an illusion. And furthermore, agency is an attribute we clearly share with many, if not with all other organisms. And let's think of the machines that we create simultaneously as extensions of ourselves, that in the sense, insofar as they enhance our functionality, and at the same time as effects our agency has on our environment. In other words, let's try thinking of ourselves in the same terms as we think of other organisms. Organisms that shape their environment by their activities, and also that build entities extending their functionality and hence can be thought of as extensions of themselves. Think, for example, of beaver dams, or of bird nests, or of any of Scott Turner's wonderful examples of the tunnels built by earthworms that serve as accessory kidneys, of the bubble gills built by aquatic beetles, or the horn-shaped burrows of crickets that amplify song, or of homeostatic termite mounds. Now think of all these systems as self-organizing systems. That is to say, think of a system in which the entire system is shaped by the combined activities of all the individual components. I think this comes close, a lot closer than recent conceptions of self-organization to what Kant originally had in mind. These activities are generated inside individual components with effects manifestly external to themselves, but all the while remaining inside the composite self that defines the larger system. The modifications engendered by these activities do not need to be random, and in general will not be random, but nor do they need to be aimed at the coherence or survival of the system. That is to say, and here I depart from Kant, they don't have to be for the sake of others, they simply have to have effects on others. It's just that those modifications that do enhance the survival of the system will be the ones that, by definition, will persist. Now, this might lead us to think of everything as a self-organizing system, but doing so need not be bad, as long, that is, as it comes with the understanding that the most interesting kinds of self-organizing systems are not those of uniform systems, but rather those that require the participation and interaction of many very different kinds of cells. Here, in the heterogeneity of cells, lies both the essential point and the rub. Especially the rub lies in the very different kind of self and different order of agency that human participation ushers into ecosystems. For we humans have perfected agency to such a degree that the effects of our participation threaten a degree of destabilization that far surpasses the power of all other species to destabilize their and our ecosystems. There is, in other words, there is indeed cause for worry about our impact on our environment, but not because human intentionality is in a different realm from the agency of other organisms, but rather because the perfected form of agency, the perfected form of our agency makes it ever so much more consequential. Thank you.
Thank you very much, Evelyn. Now Simon Levin.
Thank you very much, Jim. And first of all, I want to thank Jim for inviting me and for putting together this fascinating program, especially inviting my old friend Evelyn Keller. We've known each other for 35 years, and so it's really a great pleasure to be here. And I want to take the liberty also to dedicate my remarks tonight to Edward Leifer, my father-in-law, who passed away last night, and to my wife Carol, who sits here in her grief. It's very hard for us, but I think the topic is one that's appropriate in these times. So I will have him in my mind as I talk. So, as Evelyn said at the end of her comments, ecological systems are at risk. We're losing biodiversity. We're losing the services that nature provides us. There's even concern that that ocean circulation patterns are at risk. And hence it's natural for us to ask questions like, what are those features, those macroscopic features of systems that are of importance? In particular, how has evolution shaped these? And what is it that stabilizes them? This has been a topic of great interest. Evelyn cited a number of different efforts, and I'll come back to most of those that she mentioned, to characterize these. One is the idea of James Lovelock, inspired by the goddess Gaia, that Earth's system represented an organism. He was in this inspired by James Hutton, who was often thought of as the father of geology. James Hutton said, "I consider the Earth to be a superorganism, and its proper study should be by physiology." Lovelock also specifically attributes inspiration to Alfred Lotka, who's also known as one of the fathers of theoretical ecology. Lotka wrote, "It's not so much the organism or the species that evolves, but the entire system. Species and environment, the two are inseparable." And that's a notion which I think has more and more traction among ecologists and evolutionary biologists today. It's come to be called the niche construction, namely that the organism is inseparable from environment. So what is the Gaia hypothesis? Well, Lovelock proposed that the biota actually control their physico-chemical environments at just the right condition for its survival. But the concept of Gaia itself evolved. In a later paper, together with Lynn Margulis, Lovelock wrote, "The Gaia hypothesis views the biosphere as an active, adaptive control system able to maintain the Earth in homeostasis." In the extreme form, then, the biosphere became a superorganism, selected for its macroscopic properties. This is what Jim Kirchner calls teleological Gaia, where Lovelock and Margulis wrote, "The Earth's atmosphere is more than merely anomalous. It appears to be a contrivance, specifically constituted for a set of purposes." Now, the problems with this approach, especially for an evolutionary biologist, are that Gaia seems to be dealing with the macroscopic properties of the whole system, but that's not how evolution works. Evolution operates at lower levels and not for the benefit of the whole system. Lovelock, in his writings over the last several years, has come to explicitly acknowledge this, to indicate that his early formation of these concepts were therefore flawed, and that one needs to modify these approaches. In its extreme form, Gaia really ignores what the physicists call the anthropic principle. Lovelock, for example, and this was just 4 years ago, writes, "We have a cool, wet planet with an unstable atmosphere that stays constant and always fit for life. The odds against this are close to infinity." In other words, what's the chance that just the right system for us to survive and for the biosphere to survive happens to be here? Well, the anthropic principle starts from this question: is the fact that Earth supports life really infinitely improbable? One has to consider the observer bias, namely the fact that life is here, and in particular that we are here, to observe the conditions is because those conditions are right. And if one tries to compute these probabilities after the fact, it's like saying, what's the chance that all of us would be here tonight? Well, you can't ask that question after the fact and compute it as an unlikely event. Of course, in a certain way of computing things, it's an unlikely event, but so is every event. A somewhat different view is the one that Evelyn referred to, that Per Bach developed, namely self-organized criticality. This is a quite different notion. And Evelyn described these sand piles. Per Bach unfortunately passed away a few years ago, but he was a brilliant contributor to thinking about self-organized systems. His notion of self-organized criticality, these, by the way, are two real sand piles from a shrine just north of Kyoto. And you see that both shrines are close to this critical angle that Evelyn described, but one of them has just undergone an avalanche. Unfortunately, Per Bach is not there really dripping sand to restore this sand pile, but his idea is you keep dripping sand and these avalanches will maintain the system near this state of criticality. And here's a picture of actually grains of rice rolling downhill. The idea is that the steeper the sand pile becomes, the larger the avalanches. And therefore, self-organized criticality predicts power law distributions of avalanches, and then when applied to ecological phenomena of extinctions, such as you see here. But as Evelyn pointed out, This is not the only way power laws can arise, and simply the observation of power laws is no indication that this is the mechanism that's responsible for them. So the problems with Gaia, or that Gaia treats the biosphere as if it were selected for its macroscopic properties, and even though Lovelock recognizes the need for models that incorporate selection at lower levels of organization, there's no reason to expect that such selection should optimize the global properties of systems. I think that's a fascinating research question. What's the difference between systems that have been selected for particular properties and those in which selection is operating at lower levels of organization? But there's certainly no guarantee or even expectation that that lower level selection will optimize system properties. It's not even clear what it means to optimize system properties. As far as self-organized criticality is concerned, although it doesn't assume any macroscopic optimality, like Gaia seems to suggest, Per Brock described this self-organized criticality as simply an attractor of a dynamical system. But it ignores selection among system components. A sand pile is made up of an ensemble of identical grains of sand. It has no diversity. It has no modularity. These are key properties of natural systems, and they're key to the robustness of all complex adaptive systems. This is missing in the theory of self-organized criticality. So the truth, I think, as Evelyn indicated, is somewhere in between. Namely, ecosystems, however they are defined, self-assemble. But they self-assemble from components that are shaped by evolution. So there's an emergent nature to ecosystems, but that's not separate from an evolutionary concept. Evolution is going on, but it's evolution among the components. So there's an interplay between evolutionary processes and self-organizing, self-assembly processes going on at different scales of organization. That evolution that I'm talking about, however, is not driven by the fitnesses of the systems as wholes, but rather driven by the relative fitnesses of the components that make up those systems. But it's true that evolution can act at intermediate levels, as in mutualisms, as in ant colonies, as in beehives, and even in multicellular assemblages. Indeed, multicellularity, in which different kinds of cells come together and form an integrated organism. Multicellularity, a topic which has been of fundamental interest to my colleague John Bonner for half a century, has arisen many different times over evolutionary history. We have lots of examples of multicellularity and differentiation arising. One might ask, are human societies another example? Well, as this picture illustrates, if they are an example of multicellularity with cooperation among individuals, they're not an example where evolution is working for the good of the whole. Thus, indeed, although evolution can act at intermediate levels above the level of genomes and organisms, as the level of organization increases, from the cells to the organism to the population to the community to the ecosystem to the biosphere, the integrity of the unit becomes fuzzier, it decreases, and therefore the efficacy of selection decreases. As the unit becomes more loosely defined, you don't have something that evolution can operate on as a whole. So what then accounts for the persistence of the biospheric patterns that are so important to us that I accounted for at the beginning? Ecosystems in the biosphere are, as Evelyn mentioned, what have come to be called complex adaptive systems. That's perhaps an unfortunate term because it seems to imply that the systems are adapting and therefore are being selected. What it really means is they're made up of adapting units. They're made up of heterogeneous collections of individual units that are operating usually for their own benefit, that interact locally, and that evolve based on the outcomes of those interactions. That evolution doesn't have to be a genetically based evolution. It can be a cultural evolution. It can be organisms getting together in an orchestra to make an integrated whole. or a herd of animals changing their behavior in order to provide an integrated whole. And in the left, they're doing it because they want to be an integrated whole. On the right, they may be, the integrated whole may be an epiphenomenon, the result of local interactions entirely. In complex extractive systems, therefore, we can't be satisfied with holistic approaches like Gaia or self-organized criticality, because individual agents are driving evolutionary change from the bottom up. And the system evolution emerges from the interplay of processes that are going on at many different scales. So in understanding how such patterns arise, we have to think about what the levels of selection are. The levels of selection are key. For example, the cell cycle is an important property to organisms. It's something that has been selected, that selection can operate on as a whole, because a breakdown in this process reduces the fitness of the organism and therefore will be a target for selection. But if we look at a different kind of circular causal network, namely an ecosystem, here there is no similar sort of selection operating on the system as a whole, and so an ecological food web is something that has been formed by bottom-up processes. There's been a recent literature involving, in particular, the work of Jeffrey West and Brian Enquist and James Brown in New Mexico, trying to understand the branching patterns in our bronchia, in our cardiovascular systems, for example, in terms of an optimization of function, of a distribution of gases or fluids, subject to certain constraints. And I think that there's a lot of merit in these approaches in thinking about how would one best describe a branching network to achieve particular functions. But we see branching networks like these bronchial trees in many other situations, and it's tempting to take the theories that have been developed, the optimization theories, and extend them to these other situations. For example, to the branching patterns one sees in trees. In both situations, one can describe this functionally with a main branch with a certain probability of branching, a main trunk with a certain probability of branching, and on those branches the same probability of branching, etc. So we get these self-similar patterns, and by changing the parameters a little bit, we get the different sorts of tree patterns that you see here. So why not apply those same theories that have been applied to the bronchial tree to real trees, either above ground or to their root structures? And indeed, this has been done. But these trees look different than the trees on the preceding slide. And one of the reasons they look different is that a real tree is not enclosed in somebody's chest. And one of the ways that you can succeed in evolution, if you're a tree, is not just by finding the best way to capture sunlight, but also by interfering with the ability of your neighbor to capture sunlight. So a branching pattern of a tree can serve two purposes. It can help to capture sunlight, and it can also shade other individuals. And the difference is then, first of all, that these patterns are more diffuse. They're not as space-filling as the bronchial trees. And secondly, it requires not an optimization approach, but a game theoretic approach. What's best now has to be understood in a game theoretic situation about what other individuals are doing. And in fact, most of the situations we confront in evolutionary theory are game theoretic problems. Well, one also sees these sorts of patterns in riverbeds or in erosion patterns. And here, once again, we see a branching network with a main trunk and certain probability of branching, et cetera, self-similar patterns. My colleague Ignacio Rodriguez Iturbe and Andrea Rinaldo have documented in their wonderful book. But this is a very different situation yet, because here selection is not operating on any whole organism. There are optimization processes going on, but they're all local, describing how water can best find its way, for example, down gravity gradients. And so here we really are dealing with a property of emergence. So we see the same patterns, the branching structures, arising in different situations, and you can extend this as well, for example, to phylogenetic trees, to the evolutionary trees that people study. These are emergent patterns. There's been no selection operating on an evolutionary tree. Indeed, there can't be. The fact that one sees similar patterns in different situations doesn't mean that they have similar explanations. The level of selection, where selection is operating, whether it's operating on the whole system or whether it's operating at lower levels, is crucial and produces different patterns. And you can see that the much more spread out pattern of the river basin, even than of the trees, which are more spread out than of the bronchial trees. As Evelyn pointed out, the ecosystem itself is not a real thing. It's not a unit of selection. It is, to some extent, in the eyes of the beholder. An ecosystem is not an organism. It's what we choose to define it to be. It's to some extent, therefore, culturally defined, and to some extent an abstraction, indeed a metaphor. Evelyn mentioned the work of Frederick Clements, and I asked the question here, do communities and ecosystems even exist? The picture that you see here, taken from the book of Robert Whitaker, contrasts the ideas of Clements, which you see at the top, from the later ideas, well, from the ideas that became favorable later, but actually were present in competition, of Gleason. Clements' idea was that ecosystems and communities looked like what you see at the top. Now, what are we looking at here? These are distributions of species along gradients, for example, altitudinal gradients. And each one of those curves represents a different species. In Clements' view, species came and went at particular ecotones along these gradients, and so one would come to a particular point and a group of species would drop out and a new group of species would come in along the gradient. That's the Clementian view. If that were the case, then each clump of species could be thought of as a community, and that community could become a superorganism on which selection could operate because those species interacted with each other on a regular basis. The ideas of Gleason, however, which were nowhere near as popular in their time, but much more popular today, was that species had, as in the bottom, individualistic distributions along those gradients. So that as one moved along the gradient, one species would appear and another would disappear, but each species had its own distribution, and there was no clear point at which a group of species came and another group of species went, and therefore whatever we chose, pass me some of the water. Whatever we chose to, thank you, to call a community or an ecosystem was an arbitrary subdivision of a continuum. The ecosystem is an abstraction. It's, in this case, something that, a perspective that we imposed on nature. And Robert Whitaker's work in the Smokies and in the Siskiyous, looking at species along gradients, showed that indeed the Gleasonian view was in general much closer to the truth. And that's the view that's more prevalent in ecology today. Ecologists recognize that communities and ecosystems are not integrated units that are targets for selection. Self-organizing systems, indeed, through this selection at lower levels, may become either more stable, can become more stable and more robust. Now, what is this image that I'm showing you here? Imagine a truck, an old truck, loaded up with junk and spare parts hanging on it, going down a bumpy road, and as it goes down that road, pieces fall off. Eventually, if the truck keeps moving, pieces stop falling off. What's left are the pieces that make for a more robust entity. There has been a process, if you will, of selection, eliminating the less stable pieces, and along the way, in some sense, the system becomes more stable over time. Things stop falling off. There hasn't been any evolution going on at the level of the whole system, one can't say the system has become more robust because it's been selected to be more robust. It's simply developed a robustness along the way as the less robust pieces have fallen off. But this process doesn't have to lead to a more stable system. Indeed, this taken from the Darwin Awards from a few years ago that some may know about, is the idea that selection, because it's not operating for the benefit of the whole system, the way evolution works by natural selection can ultimately lead to the death of the system, to the death of the species. And indeed, one has to ask whether we're doing that to ourselves today. It's quite clear that we engage in processes in which individuals, by following what seems to be their own self-interest, are ultimately contributing to the potential destruction of the system. That's what we're doing to our biosphere. So the central question remains, how are ecosystems organized? Patterns emerge in these complex adaptive systems to a large extent from phenomena that are going on at much lower levels of organization, at the level of individual agents, at small spatial scales, and at short temporal scales, and these lead to the emergence of pattern systems as a whole. What does self-organization mean? This was the central theme of Evelyn's remarks, and I'm hoping that we'll come back to this in a discussion. When we're talking about self-organization, do we mean the global emergence of some sort of pattern from rules that are in some sense local in space or local in terms of interactions? Does it require that we understand where the rules come from? It's a question I'll come back to. And are multiple outcomes possible? As I listened to Evelyn, I thought about three different cases. One would be the case of a design system. Another would be a case of the biosphere, which I think of as self-organized, although there's some subtleties that we'll come back to, I'm sure, in the discussion. But the third is a case of an organism developing from a set of local rules that have not necessarily been designed, but have been shaped by natural selection. The rules of development in which an organism arises from a homogeneous egg without any patterning information initially, simply because by a set of local rules of interaction. Is that a case of self-organization? Indeed, we start from this random assemblage, and the system eventually develops a regular pattern, but except in pathologies, it develops more or less the same pattern all the time if you do this experiment over and over again, and it does so because the local rules have been specified. You can imagine also a similar situation in which Frank Rosenblatt, whom Evelyn mentioned, or Ashby, have specified the rules as the designer and allowed the system to self-organize. Is that self-organization? Is that different than a situation like the biosphere, in which presumably nobody has specified the rules? But I'll come back to that theme. So an important question is the existence of multiple outcomes of this process something that is a requirement of self-organization? And that's really a question I have for Evelyn, because it's a question I've worried about for a long time. Evolution, you see, and describes what Francois Jacob would call a process of self-organization. In a wonderful paper in 1977 called Evolution and Tinkering, Jacob pointed out that because multiple outcomes are possible, because we're constrained by past history, evolution is really the work more of a tinkerer than a master craftsman. We have 2 arms and 2 legs because our predecessors crawling up out of the sea had 4 limbs. So there are historical constraints. One of the most fundamental axiomatic approaches to mathematics principles, the principle of induction, works in this way. The principle of induction says if a proposition is true for n equals 1, and if we can show that it's that whenever it's true for a particular k, it's true for the next k, then it's true for every positive integer. So this has the ingredients of having to start the process and then having to evolve the process. So from local rules, global pattern can arise. And this has been a universal theme in the physical sciences, in the biological sciences, in linguistics, where Chomsky's grammar, for example, thinks about the local rules and how they lead to the patterns of sentences and paragraphs and whatever. And more recently, I think, in the social sciences, in economics, for example, and in anthropology, how cultures arise and how economies emerge from local interactions. Does the number system self-organize? The first advanced math course I took helped me to understand the construction of the natural numbers. It went like this, just mimicking the principle of induction. 1, we'll suppose there is a natural number called 1. We have to posit that to begin. And then we'll assume that every natural number has a successor. And once you have that, you build up the number system. So in this sense, the natural numbers are constructed. They, in a sense, self-organized. In dynamical systems theory, the general approach is to say, first of all, you have a set of initial conditions, and then you have a set of dynamical rules. And from those initial conditions and those dynamical systems, you evolve the system. If those rules are right under certain conditions, there'll be a unique solution. But under other conditions, you get bifurcation and uncertainty. The system can split. Initial conditions, dynamical rules, possibility of multiple outcomes. Spatial stochastic processes, which occur in many different places in science, also begin from local rules and a particular set of initial conditions and allow pattern to develop naturally, as you see here. So I claim that natural selection and theories of evolution do extremely well at explaining the inductive step, the developmental step in dynamical systems. They tell us how we get from the initial conditions to the patterns that we see in nature. And that's what the theory of evolution is all about. But they have nothing to say about the initial step, the Big Bang, basically. In other words, it tells us how the system continues to develop, but it doesn't tell us how it gets started. Therefore, they are silent on what are perhaps the most fundamental questions of theology that we've been asked to address tonight. What did the biosphere evolve from? We may have a theory of evolution that tells us how it will develop from a soup, but where did the soup come from? And also, where did the laws of nature come from? There is no designer implying the laws. There is no process that's selecting on the basic laws, including the laws of logic. Where did those laws come from? So this is close to where I'm going to leave you tonight, because these are the issues, I think, that bring different disciplinary perspectives into contact, and suggest, as Jim has in his papers, that there are complementary views to consider. That there is not necessarily a conflict between different perspectives, because they're really addressing different questions. And that, I think, is why we're here tonight, and that's where I'll stop. Thank you.